Hello, folks. I hope you guys are doing okay and that you managed to have a decent Easter in spite of everything. It's kind of weird to think that we're already halfway through the fourth quarter of the year. This week, there's really not much of anything new to explain, but we are going to review the stuff that we've done online the past couple of weeks. We learned last time that a logarithm was the exponent that you put on a base in order to get a given number for the answer. Which means if I say the log base 3 of 81, I'm asking the question, what exponent do I put on 3 to get 81 for the answer? So log base 3 of 81 equals x would be the same thing as 3 to the x equals 81. Either way, the answer is going to be 4. We also learned last time that you could evaluate logs by using the log key on your calculator and then dividing. So if I wanted to find log base 2 of 1,000, I do log of 1,000 divided by log 2. You always start with the big number and you divide by the log of the base, the one that's written right next to log. Remember, when you're doing that in a calculator, you've got to be careful to close the parentheses after the 1,000. If you don't do that, you will get a wrong answer. Here, though, we divided, and the answer is just a little bit less than 10, 9.96578. And we figured out you could do basically the exact same thing to solve exponential equations, equations where you're trying to find what the exponent is. Here the problem says 5 to the x equals 8888. I take the log of 8888 divided by the log of 5, and we get an answer of about 5.6. How you write those answers really depends on what the nature of the problem is. If you go to a couple of decimal places, you're usually going to be good to go. Here's another question where we're trying to solve for an exponent. I want you to think for a second, how would you do this one? We learned how to do it last week, but think through what would go on with this. And whenever there's more than just x, you still start exactly like we did before. I took the log of 282,475,249 divided by the log of 7. Now, because I'd planned this problem out ahead of time, this one happens to come out even. But 10 isn't my answer. What I've got to do to find the answer is take the exponent, 3x minus 5, and set that equal to 10. And so I'm going to add 5 and divide by 3. 15 divided by 3 will be 5. You can type that all straight out into your calculator without really even writing anything down. Divide the logs, then look at the exponent and do the opposites. You've got to add 5 and then divide by 3, and we end up with an answer of 5. In the past couple weeks, we've also been looking at two different formulas that you can use for growth. One of those was called the basic growth formula, and that one, it said A equals P times 1 plus R to the T power. Remember, P is whatever you start with, the number of things you start with. A is how many you'll have in the end. R is the rate of growth, which you always write as a decimal, and T always stands for time. And the other formula was the compound interest formula. It was basically just a more complicated version of the same thing. Here it says A equals P times quantity 1 plus R over N, all to the NT power. You still have P as the principal, the amount of money you start with. A is the accumulation, or the amount you're going to have in the end. R is the rate of interest. T is time. And the thing that's new in this one is N, which is the number of times things are compounded per year. So like if it was compounded monthly, that would be 12. If it was compounded weekly, it would be 52. So last week, instead of a quiz, you guys had an assignment where you were supposed to write some story problems of your own. And we're going to take a look at a handful of those here. You're also going to have a worksheet that will be online that you can take a look at some more of them. And your quiz this week will also have a few problems that you guys wrote yourselves. Now, I will warn you, when problems are things people have written themselves, you often get stupid answers. That's okay. In fact, there were some of these where people came up with answers themselves, and a few of you were actually not right on the answers you came up with. And I'll talk about that when we get to one or two of those problems as we go along. Well, the first one here, it says Derek buys 5 cars in 1 year. If it increases by 3% each year, how many years will it be till he owns 100 cars? And so he starts with 5, it grows by 3% a year. When will he have 100 cars? This one's going to involve that basic growth formula, that A equals P times 1 plus R to the T power. And again, the A is what you're going to have in the end, so 100, equals P, what you start with, which is 5, and then times 1 plus 0.03 to the T power. Now here we're solving for the exponent, so I know somewhere along the way I'm going to be using logs to solve this problem. Whenever you have problems like this though, what you always want to start with is dividing those big numbers that are out front. So the first step here was just to take 100 divided by 5. And if you do that, you get 20. Basically, what the problem would look like after you divided it is it would say 20 equals 1.03 to the T power. And that's why what I did to solve the rest of it is I just divided logs. I took the log of 20. I could have just done log and then done the answer key in parentheses, divided by the log of 1 plus 0.03. And it turns out that it's going to be 101 years before Derek's going to end up owning 100 cars. So here's another problem. It says Maya works at the Dairy Queen and puts $6,000 into an account. It's an awful lot of money to make at the Dairy Queen, but that's what it says. The account earns 7% interest compounded quarterly. How long will it take for her account to reach $30,000? Now, this problem I can tell is a compound interest problem, both because it's got money all over the place in the problem, and it also specifically says compounded quarterly. So we're going to use that formula to figure out what we've got. And again, P is what you start with, A is what you end with, R is your rate of interest as a percent, T is time, which is what we're trying to find, the how long, and N is the number of times it's compounded per year. So here what the equation is going to look like is 30,000 equals 6,000 times 1 plus 0.07 over 4, all of that raised to the 4th T power. You always end up with that N, here 4, both on the bottom of the fraction and also in the exponent. That same number has to come up both places. And again, just like the last one, I'm going to start by dividing big numbers and then I'm going to divide some logs. So this problem, I started out by doing 30,000 divided by 6,000. And after I did that, what I'd have is 5 equals those parentheses to the 4t power. So if you look really closely at that second line, I actually have one more thing going on there than I did on the previous problem. I took the log of that answer I just got, divided by the log of the parentheses, 1 plus 0.07 over 4, and then I divided by the 4 that's in the exponent. I could have done that on a separate line, but it's easier just to do it all at once. If you're careful that you close both sets of parentheses, that's going to end up being important. Now here we would get an answer of about 23.2 years. So it's going to be a while before she has 30,000. But on the other hand, if I could quintuple my money in 23 years, that's not doing too badly. Another problem here, and you can tell I mostly chose some of the ones that people had chosen to illustrate. We have a garbage man collects 3 bags a minute. Every year, he collects 10% more bags a minute. And our question says, how many years for him to collect 5 bags a minute? So all we're doing is going from 3 to 5, which doesn't seem like it ought to be all that long, except it's only going up by 10% a year, so it's going to take a while before we get all those bags. This one, there's no money and there's nothing that says compounding, and that's why I know it's going to be the easier of the two formulas. Again, we got what we have in the end equals what we have in the beginning, 1 plus the rate all to the t power. So 5 equals 3 times quantity 1 plus 0.03 to the t. And to solve that, I start by taking 5 divided by 3, and then I've got to divide the logs. Log of that divided by the log of the parentheses. This time I don't need to divide by anything else because there's nothing in the exponent. Once I've divided the logs, I'm done. And we get about 17.3 years. So our next problem specifically says that it's compound interest. It says Doug puts $7 in his account. And you can see those $7 that are circling around him. It earns 10% interest compounded daily. When will Doug have $300? And every interest problem looks something like this. You start with a certain amount, we want to know when you're going to have a certain amount, and we've got to know the interest and how many times a year it's compounded. When you plug into the interest formula, you'll have something that looks kind of like this. We got 300 equals 7 times quantity 1 plus 0.10 over 365, all of that raised to the 365t power. Again, the basic idea of what we're going to do is we'll take 300 divided by 7, and then we'll do the log of that, divided by the log of the parentheses, divided by 365. So for variety this time, I actually showed you some screenshots of the calculator that's built into Windows. If you just go to the Start menu in Windows, you can always find a calculator there. When it comes up normally, it just looks like a calculator you would have used in first grade, but if you choose scientific, you'll get a display that looks like what you see on the screen. You notice here I did 300 divided by 7, and I got about 42.85. Now, the Windows calculator is honestly harder to use than most other ones, because what I've got to do is kind of do things in steps. If you look at what's going on the screen, all it says is the log of that number that I just typed in there. All I did to make that happen is I just hit the log key. I didn't type all that stuff in parentheses. I just took the answer that was there and I hit log, and it tells me that's about 1.63. The problem is I can't just take that and divide by the log of the parentheses like I can on most calculators. What I had to do was to write down that number, and now what I'm doing is working out what's in the parentheses, 1 plus 0.10 over 365, and then taking the log of that. And you notice I get like 1.189, some change like that. But there's something really important about this, which is that at the end of it, it says E minus 4. What that means is this number is actually in scientific notation. This is the same thing as 1.1896, etc., times 10 to the negative 4th power, which means it's really 0.00011, etc. You go from there. So finally, I'm actually solving the problem. What I did first is I divided those two numbers I just came up with. I took the number I got when I took 360 divided by 7 and did the log of that, divided by the log of the parentheses, so 1.63202 divided by 0.00011,896. I divided those logs, and then at the very bottom, I took that divided by 365. And my final answer is 37.6. Now, I said at the beginning of this that I did that for variety. Actually, I threw that in there because I record the sound for this on a different computer than I make up the PowerPoints, and I realized when I was recording the sound that I'd actually screwed up the equation on this, and so what I'd originally done on my built-in calculator on that computer was wrong. So I went back and found a way to solve it, and it does turn out that, yeah, about 37.5, 37.6 is the right answer. We're going to look at one last problem here. And I'm going to tell you that this happens to be one of the problems where I saw that the person that wrote it did an answer on the sheet they turned in, and actually that answer isn't quite right. So no offense to that person, but we're going to find what the right answer actually is here. The question says Algona's population is roughly 6,000 people. It grows at a rate of 3% each year. If this continues, what will Algona's population be in the year 3000? Now, this is actually kind of an interesting question, and it's different than everything else that we've looked at today. That's because what they're asking is, what's the population going to be? They're asking for the A that goes over on the left-hand side of the problem, the amount we're going to have at the end. We know what the time is, or at least we can figure it out pretty easily, but we need to find that A. So if you look at the calculator screenshot I put over at the side, you notice what I did is I took 3000 minus 2020. And that's because I wanted to figure out how many years is it from now until the year 3000, and it turns out it's 980 years. So my equation ended up being 6,000 equals 1 plus 0.03 to the 980th power. That's the problem that we've got to solve. Now, before I show you the answer, I want to point out that there are some things about this problem that probably in the real world you wouldn't necessarily find. First off, it says 6,000 people in Algona, and that's actually pretty close to right. So that number's fine. It says 980 years, which is kind of telling me we're going to get a really big answer once we get done, because that's a long, long time from now. Algona's been a town for like 160 years, so we've got a lot more time to go before we get to 980. The other thing that I'm sure seemed really reasonable when they wrote this problem, but it really isn't a terribly sensible number to start with, is that 3% rate of growth. If Algona's growing at all, it would probably be by way less than 1% a year. 3% is a ridiculously high rate of growth. Third world countries with tons of people don't grow by 3% a year, and certainly nowhere in the American Midwest is going to grow that fast. However, we're going to go with what that problem says, and we're going to leave all the numbers exactly as they are. All I'm going to do basically is take this, type it into the calculator just like it looks, and I'll have my answer. You can see I did type in 6,000 times 1 plus 0.03, all of that raised to the 980th power, and what we got is 2.283660087 E16, which means 2.28 times 10 to the 16th power. That means after the 2, there's 16 places until you get to the end. So the number that we are looking at in this problem is going to be 28 quadrillion, 366 trillion, 8 billion, 700 million people, which would be a whole lot of people if it kept growing at that rate for 980 years. Now, the place we got this from said there were going to be about 24,000 people. And I'm pretty sure they did not really look at how long this difference was, and that's okay. I mean, it's no big deal. I didn't count anything off on the problems, and just, kind of got a laugh out of both that answer and what the real answer were. But again, all you do is type it in like it looks, and we get a great big huge answer. So again, there's really nothing new this week. What you do want to do is take a look at a worksheet that's got some of the other problems that people wrote on it. And by the way, if you happen to be someone that didn't turn in your problems from last week, you do still want to get those in because that is going to count towards your grade and you do want to do it. Plus, you can get some easy extra credit for doing things like illustrating the problems. There also will be some problems that you're going to need to work out when you get to this week's quiz. So you do want to make sure you know how to do those interest problems and the general growth problems. And I chose to finish all of my videos this week with the same little thing here about kindness. You might actually remember seeing this on my bulletin board back at the very beginning of the year when I had a bunch of sort of inspirational quotes up there. And this actually was one of them long before anybody thought about pandemics like what we have now. But it is kind of a good thing to think about, I think, to just realize that we can spread around kindness and make a good pandemic. So let's do that, and you guys have a good week.